Hello everybody, welcome to the Falling Walls Lab MSCA 2022 edition. Please take a seat, make yourself comfortable. We're about to start. Perfect. Welcome again to the Falling Walls Lab competition, a great competition taking place yearly since 2017. Each time it showcases the quality and diversity of the most innovative minds taking part in MSCA projects. And the winners of the MSCA competition will compete as MSCA Fellows for the Breakthrough Winner of the Year at the Global Falling Walls Lab finale. It will be in November 2022 in Berlin. Now, in a few minutes, we're going to have 15 MSCA Fellows who will tell us about their research in 3-minute videos. And they will do that in front of a 6-person jury and in front of you as well. So you will be able to pick who, in your opinion, is the best contestant. Now, to launch the competition, we are delighted to have with us the president of PSL, Paris Sciences et Lettres University, which organizes the whole MSCA conference, Mr. Alain Fuchs.
Thank you, and good morning to everyone, ladies and gentlemen. Welcome to everybody, either online or on site. It's a great honor to host and launch, together with Director General Themis Christophidou, the 6th edition of the MSCA Falling Walls Lab competition at the Institut Curie, here, member of PSL University. It turns out, by the way, that I'm a great fan of the Falling Wall Conference, which is being held in Berlin every fall, celebrating, so to say, the wall, the Berlin Wall falling. It's an extraordinary event, really, and those of you who will be able to attend this extraordinary event will be very lucky. Yesterday we were dealing with the future of MSCA program and its impact on the future generation of researchers. It was a very lively and extremely well organized meeting yesterday. Thank you very much again to the organizing committee. Today, 15 representatives of these new generations take the opportunity to showcase their innovative ideas and projects to the scientific community and explain how their research helps to break down walls between science and society. I'm particularly happy to see that women, who were widely mentioned yesterday, are in the majority among this selection. These 15 talented young researchers from around the world each tackle some of the major issues facing our countries, whether they be health, environmental, or cultural. They are a perfect example of what science can do for our fellow citizens, but they're also, and above all, the best bulwark against ideology and the rule of opinion, which can be seen around the world and jeopardize the implementation of effective solutions. It is indeed our duty to communicate to citizens and leaders in the public and private sectors the full importance of scientific method and the urgency of engaging with the most up-to-date and rigorous research findings. There is no other way out. This cardinal mission of the university is perfectly fulfilled by our brilliant young colleagues here today. And whatever the jury's verdict, we are all pleased to see that the next generation is assured at the highest level, that they all are motivated by a strong desire to be useful. The high quality of the projects and the extraordinary diversity made the jury's verdict difficult, and a choice has to be made. Still, whatever the jury's verdict, I would like to offer them all, and offer you all, my sincere congratulations and encouragement for their future career. Thank you very much.
Now the Director General for Education, Youth, Sport and Culture of the European Commission, Mrs. Themis Christophidou, is here with us as well. Can you hear us, Themis Christophidou?
Good morning, Paul. Yes, I can hear you.
Fantastic. Thanks very much for delivering your speech, and thanks very much for being here with us this morning.
I thank you, dear President, dear members of the jury, ladies and gentlemen. I would like to greet you all online and on site, and of course, greet in particular our 15 MSCA fellows who must be very impatient to start the competition, and so are we. I feel so fortunate to be part of this day again, like in previous years. It's a privilege. I promise you I will be brief, but I would like to share the latest developments from the side of the European Commission with you. First, we have a brand new fellowship scheme in the MSCA work program for 2022, the MSCA for Ukraine. This means that we will now be able to provide fellowships to displaced doctoral and postdoctoral researchers from Ukraine so that they can continue their work in one of the European Union member states. As in other MSCA actions, the scheme will provide family allowances for researchers' families as well. And once the war is over, and we all hope that this will be sooner rather than later, they will be able to use MSCA for Ukraine to re-establish themselves in Ukraine, to rebuild the country's research and innovation capacity. The budget for this action is 25 million, dedicated only to this. I'm personally proud of how quickly our teams mobilized to obtain this support for refugees from Ukraine in the education and training sector. MSCA for Ukraine is part of this response, which covers early childhood education, schools, vocational education and training, universities and research, and I hope that many scientists will also be able to benefit from it. And we have something else which is new. We have decided to invite researchers to join classrooms in primary and secondary schools where they can discuss their work with pupils. For example, within this idea, some of the projects will propose researchers to receive training before their visit and learn about how to communicate their work best to a younger audience. And they will still, before the visit, present their research topic to the resident teacher so that they can assist in and follow up on the presentation. Many other types of activities will be proposed to strengthen the direct interaction between researchers and pupils on the challenges our societies are facing. Because we want pupils to discover science, research, and innovation in an interactive and stimulating way. Because we want to tickle their curiosity and motivate them to learn more, to not be so impressed or intimidated by science. Maybe we can even encourage some of them to one day become scientists themselves. We need scientists, we need more of you. And we need excellent researchers and innovators to tackle current and future challenges. And even more so, dear fellows, dear contestants of the Falling Walls Lab MSCA 22, you too play a crucial role in this process. When you communicate about your research projects, when you show us the impact of science, research, and innovation, this is when you have an impact on citizens' daily lives. And this is when research becomes true science. Thank you for being here today and for sharing your passion. And I will not let us wait any longer. I believe everybody, jury and audience, we are all eager to listen to you, myself included. I wish the best of luck to all of you.
Okay, so let's start. Here's how we're going to proceed. For each contestant, we will look first at their 3-minute video, and they will, afterwards, they will answer one question from a member of the jury and one question from the audience. So you can ask the contestants your own question, and they will have to answer each of these questions in 30 seconds. Now, for those who are here in this room, this is how you're going to be able to ask your question. You need to join the video stream. You need to join the video stream on your telephone, and it's there. We're going to have the QR code, which is going to be shown on the screen. If not, it's there. It's the same. Okay, here's the QR code. All you have to do is take a picture of it, and go on the video stream. And then there in the chat, you will be able to ask your question. Okay, are we all set? Is everybody ready? The contestants are ready? Fantastic. So let's start with our first pitch. Alba Alvarez Martin is our first contestant, breaking the walls of mass spectrometry in cultural heritage. Good luck, Alba.
I want you to think about a drawing that you made for your parents when you were a kid. Maybe you used watercolors or crayons in a white piece of paper. And your parents, they were so excited and so proud of you that they hung this small piece of art in their house. And probably it's still hanging there. But it doesn't look the same, right? Probably the colors have faded and the white paper is turning yellow. So if this had happened in few years, imagine what is happening to paintings that Van Gogh, Rembrandt, Velázquez, Da Vinci painted hundreds of years ago. The color change is something that has been detected already in paintings from Van Gogh. He used to mix red and blue pigments in order to obtain purple colors. But one of those red pigments is really light sensitive and it can fade because of the light exposure. So actually what we are seeing in paintings from Van Gogh is a completely different version of what he painted like hundreds of years ago. In my research, I'm using mass spectrometry to understand the color chain of those paintings. And this is really a really complicated topic because paintings are really complex systems. We have the canvas, the pigment, the oil, the wax, the resin, and all of them, they are reacting with each other over the century and with the environment. And on top of that, conservators are adding new materials in these complicated systems, and they are also can react with the painting. So human bodies are also very complicated systems, and when doctors want to know what is going on in a specific area, what they do is take a biopsy to look more closely in the tissue. And one of the techniques that they use is matrix-assisted laser desorption ionization mass spectrometry imaging, which is a very long name, but MALDI in short. So having this idea in mind, what I started to check if I can use MALDI to map organic pigments within paint layers from paintings. And this is really, really challenging because samples coming from paintings are unique. So we only have one go. So that means that we have to work a lot in the lab because our method of analysis has to be perfect. We need to know how to handle those tiny samples, how to prepare them before the analysis, and how to do the data analysis in order to obtain the most information from them. And this is actually where I am right now. We are having really excited information because actually we are trying to understand the molecular chains that they are associating to the chain of the original color. And this is crucial information if we want to preserve our cultural heritage for future generations.
Alba, it's good to have you here.
Thank you so much.
Good to see you in person. Now, Themis Christophidou would like to ask you the first question. She's the co-chair of the jury.
Thank you, Alba. Your presentation was great. Thanks a lot. Cultural heritage and its preservation are, of course, crucial to understand the past, the present, and the future. So how do you see your approach being applied to archaeology? I'm thinking about, for example, the colors of Pompeii or the pharaonic tombs. What are your ideas?
Yeah,
Thank you so much for your question. Actually, this is a really, really good question because the techniques that I'm trying to optimize, they can be used for all kind of cultural artifacts. So it can be used for paintings, it can be used for archaeological objects. And I'm focusing in organic materials. So of course, those archaeological objects are going to have also a lot of information of the type of food, of the type of resin that they used in the past, and they are still there. They are just in a very tiny concentration, and we just need to look for that.
Thank you very much, Alba.
Thank you, Alba.
Thank you.
And I have a question from the audience as well. You know, when you play on a stage, normally you take the center. Yes, you are at the center in our minds. Okay, so. Which concrete impact could your research have?
Well,
is it just a step towards more understanding, or do you think there's going to be practical impact?
I have the mind that it has to be a practical impact. So we really need to work with cultural institutions, and we need to have a feedback for conservators, for curators. So we need to understand actually the research question that they have, and we need to adapt our science in order to have the proper answer to that. So it's really it needs to be applied in the museum.
Okay, it needs and it will be applied. Thanks very much, Alba.
Thank you so much.
Thanks very much. You can keep the microphone and give it to the next contestant. And now we will move to Reyk Börner, who is breaking the wall of climate predictability.
Have you seen The Day After Tomorrow? It's a movie about catastrophic climate change, where Europe falls into an ice age from one day to the next. Of course, this is pure Hollywood madness, but there's some science behind it. The ocean circulation in the Atlantic, which brings large amounts of heat to the north, could suddenly shut down as a result of global warming. Scientists have found that the ocean circulation has weakened over the past decades. But does that mean that we are close to a point of dramatic, sudden change? How can we predict the risk of losing climate stability? Imagine you're standing in a landscape with hills and valleys, blindfolded. What is the chance that you'll make it from point A to point B while walking around randomly? To find out, you'll have to do a lot of walking. And the more you walk around, still blindfolded, the more you'll learn about the hills and valleys of the landscape, eventually finding a path that brings you to B. But wouldn't it be much easier to just take off your blindfold and look at a map? At this point, you're probably wondering what this has to do with climate change. Well, this landscape describes the stability of our climate system. Currently, planet Earth is in Valley A, and as long as it stays there, the ocean currents will keep flowing steadily. However, there is a chance that Earth will cross the mountain pass to Valley B. The mountain pass is the tipping point, the point of no return, beyond which the ocean current stops and we enter a very different climate, the climate of Valley B. In Valley B, storms rage over Europe, New York is flooded by sea level rise, large parts of the Earth experience drought, while others suffer from heavy rain. Valley B is the day after tomorrow, just a bit more scientifically correct. So it's really important that we understand where this mountain pass is and how to avoid getting there. The problem is, we're still blindfolded. When climate scientists predict the future with model simulations, they walk around in the landscape, learning a bit more each time. But instead of walking around, my research project is about making the map. If we know the map, we will know where the tipping point is, what the most likely path to get there is, and the probability of getting there. And this could help us to prevent getting there. It's time that we remove our blindfold to learn where we're headed the day after tomorrow.
Unfortunately, Reyk Börner couldn't make it to Paris. He's the only contestant online. How do you do, Reyk?
Hello, I'm very good, thank you.
Fantastic.
I'm from Vienna.
Congratulations on this video. One of the members of the jury, Céline Bégy, is here with us. Nice to have you on board. Céline, you are a postdoctoral researcher at Université de Paris. Which question would you like to ask Reyk Börner?
Thank you, Reyk, for your presentations very well. If I understand well, you use mathematical modelization to construct the map which predicts the risk of losing climate stability. So my question is your research it's only about the theory of the modelization, or do you use real data to verify it? And if so, what data do you use?
Thank you very much for this question. So making this map is very complicated. It doesn't even exist currently for very simple models where you just approximate the Atlantic as boxes with water, kind of 3 bathtubs coupled to each other. So this is what I'm currently looking at, and that's very simple and of course far away from reality. But we hope that we can gain insight from these simple models to then interpret the output from more realistic models. And the more complex the models will get, the more closer they get to reality, and the more we can also feed them with real data from reality. But actually, we don't have much data about these tipping points. The only thing we have is an ice core record where we see abrupt transitions. But this is many thousand years ago, and we can only interpret what we see.
Thank you.
Thank you, Reyk. Here's a question from the audience. You mentioned the day after tomorrow in your video, but did you by any chance watch the movie Don't Look Up?
I have watched that movie, yes.
Okay, do you think the same thing could happen to you, that even if you predicted the exact moment of no return, no one would listen to you?
That's a very nice question, and I think that could definitely happen. But I want to take a more optimistic viewpoint. I think that's a question in itself. Let's say we find out the probability of crossing this tipping point is 2%. Is that enough to act or not? What if it's 90%? How will policy act then? So yeah, that's an interesting question, but I think there's one key difference between climate change and Don't Look Up, which is just a meteorite hitting Earth, which is that regarding the meteorite, we can't really do anything. It's also not caused by us, it's just hitting the Earth. But climate change that we see today is man-made. It's caused by us, and we still have a time window to solve it.
Thanks very much, Reyk. Congratulations. Thanks very much.
Thank you. Thanks for having me online.
So let's break the walls with Marie-Anne Ciosk, the walls of gender and race discrimination.
Hi. Have you noticed that I'm a white woman? It's hard not to. Within 1 second, we effortlessly and automatically categorize people according to their gender and race. And it's useful to group together things that share characteristics into categories. That allows us to talk about birds, rather than just robins and sparrows and those kinds of things. But the problem is that we also have very specific, inflexible ideas about what it means to belong to certain gender and race categories. These stereotypical tendencies can cause racism and sexism. Racism and sexism are bad. Most people agree on this. But then why do we still see huge racial and gender disparities in positions of power in society? 93% of world leaders, 95% of the highest earning CEOs, and 93% of directors of the top grossing films are men. And the vast majority of these men are white men. Why is that? Are some social groups, like women and people of color, just inherently less interested in or less talented in fields like politics, business, and the arts? Or maybe, as a society, we're still a bit more biased than we realize. I've researched the underlying psychological factors that perpetuate subtle biases and result in systemic discrimination. One of the ways I do this is by examining prototypes, or who people think is the best or most typical representation of a category. When thinking about birds, people tend to think about robins before penguins. Likewise, when people think about women, people tend to think about white women. And when people think about black people, people tend to think about black men. There's a hidden hierarchy in our default mental representations of people. And this has serious social consequences. People are less likely to remember what a non-prototypical person said, and are less likely to label an incident as sexual harassment if the woman is non-prototypical. And because white men are prototypical of both their gender and race categories, it seems more natural that they represent people as world leaders, CEOs, and directors. To address this problem, we need to understand why some people are considered better prototypes than others. One possible reason is that some social groups outnumber others, but this doesn't explain why men are considered more prototypical than women. In my current research project, I investigate how social power dynamics relate to prototypicality. We don't normally challenge our familiar default ways of thinking, but by becoming aware of these hidden psychological processes and their causes, we can confront them directly, design more effective policies for gender and racial equality, and learn how to see ourselves and other people a bit more clearly.
Marianne, thank you very much for being here with us today. Themis Christophidou has a question for you.
Hello, Marianne. You can hear me?
Yes, we can.
Yes, I can hear. Yeah.
Great. So I went off to study engineering 40 years ago. So the issues of gender bias are very close to my heart. People, discrimination, bias. Did you observe or do you expect a difference in what you call the hidden hierarchy between adults and children?
Yeah, that's very interesting, how adults and children would perceive these different social groups. Yes, while we still see that everyone, all humans have sort of like an evolutionary adaptation to categorize things. So we would still see that children also make these differentiations between race and gender. But I don't think we would see as strong of the prototypes in terms of the stereotypes that are associated with each group. So while people tend to have preferences for their in-group, I don't think the prototypes would be as strongly developed at this stage without as much training in society.
Thank you very much.
Thank you.
Thank you very much. So I've just been sent the new question.
Okay.
Okay, here it is.
Really?
Yes. What do you think I'm going to do with this? Okay, so let's start. I haven't read it yet. When you say that the reason many white men have positions of power, you suggest that this is because we are more biased than we think. This is interesting. But should we not consider the fact that these white men, for historical reasons, belong to socio-economic power blocks generated by historical dynamics, ruled by these very white men? They were not elected by the people. History didn't go through a democratic process. It's a matter of power. Shouldn't we focus, in order to change the situation, on changing the historical and social dynamics? Doesn't it seem more likely that changing the social dynamics will also change what you call prototypicality and not vice versa?
Okay, so if I understand correctly, because historically we've had an overrepresentation of white men, we should be focusing on changing the history?
Yes, the social dynamics.
The social dynamics. So, I mean, I think this is one of the really challenging parts of this research is that when you think of these different groups, then white men also come to mind because they have historically been overrepresented, because they've had more privilege in society. So it makes it easier to conjure the image of, famous scientists. You think about white men typically. And so it's difficult to change history, of course. So I think now as a society, you do see more of a push to having a representation of like women and people of color, in these positions to try to normalize it in a way, to try to show that these are the images that can come to mind. When you think about a president, maybe it doesn't have to be a white man immediately. So I think changing history is really tough. And I see that there's a lot of interventions or policies that are trying to target representation specifically.
So it's happening.
I think, yeah, we have some good ideas to get there.
Perfect. Thanks very much.
Yeah, thank you.
Marianne, I'll let you keep the microphone so you can give it to the next contestant. Big round of applause for Marianne, please. Let's move on to Miguel Fernandez de Ullivarri, who breaks the wall of antimicrobial resistance.
Did you know there is a growing threat that could kill 10 million people per year by 2050? What do you think it could be? War? Heart attacks? Maybe a new pandemic like COVID? I'm gonna tell you what it is. Antimicrobial resistance. This phenomenon occurs when microorganisms change and adapt to the presence of antibiotics, becoming more resistant to them. 10 million people per year and around 80 trillion euros in cost according to WHO. That's shocking. But there's a fact that shocks me even more, and I'll get there in a minute. This little fellow here is my daughter Sol. When she was 9 months old, she caught a really bad gut infection by the bacterium E. coli, and she was in really high pain for around 3 days. Luckily, she recovered after an antibiotic treatment. But imagine for a second if she got infected by a multi-resistant bacterium instead. I tell you the story would be totally different. So now let's talk about that shocking fact. It's the idea that the same gut infection, or maybe just a wound in your finger or in your foot, could be able to kill you in the near future as antibiotics become less and less effective. That's how I realized that we need to find real solutions for this rising threat. However, not everything is bad news. We have a killer solution for this problem. The killer peptide. This is a novel antimicrobial molecule composed of a few amino acids that is able to effectively treat stubborn infections while also activating your immune system, and without the side effects that the current antibiotics have. It doesn't produce antimicrobial resistance, and it doesn't affect your body or your healthy microbiota in the process. However, we didn't stop there, and we went even further, and we created a novel technology able to increase the antimicrobial potency of small peptides like this one. So take a look at this picture of this dense biofilm of Candida albicans. Imagine for a second that you had this pathogen in your body. Wouldn't you like to get rid of it as soon as possible? I would. Well, you'll soon be able to do so with a single shot of our optimized killer peptide. There are still many studies to be done, but we are making great progress and we are eager to make it available for society, because we know that little molecules like this one can make big changes to break the wall of antimicrobial resistance. I'll do it for her. Who will you do it for?
Come with me on stage, Miguel.
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 Thank you. It's
Perfect.
it's okay.
Okay.
Thank you.
Try my best.
No worries.
Miguel, Anwesh Bhattacharya, who is a finalist of Falling Walls Lab MSCA 2021, is online to ask you the first question.
Right. Hello, Miguel. So thank you for your nice presentation. What do you think is the biggest challenge in bringing killer peptides to clinical use? And also, how do you ensure that these do not become resistant themselves?
Oh, that's a very interesting question. Thank you very much. The biggest challenges, of course, is to first to try to demonstrate that the killer peptide is actually safe in clinical trials. So we are in now preclinical trials, trying to continue with all the steps and the regulatory steps. So once we get in clinical trials, we will be completely sure that the peptide is completely safe, of course. And sorry, the second question was, sorry, the second part, I don't remember.
Yeah, so how do you ensure that these do not become resistant themselves?
Yeah, because there have been many studies carried out on this peptide, and they have demonstrated that different mutations on the bacteria that could make the bacteria or the fungi resistant to the peptides, they are not compatible with viability of those microorganisms. So that's basically how it's demonstrated that the peptide doesn't produce antimicrobial resistance, doesn't induce antimicrobial resistance, sorry.
Thank you very much. Thank you very much, Anwesh.
Thank you very much.
I will talk to you later. Miguel, here's the question from the audience. I think it quite relates to Anwesh's question. So you are telling us that no pathogen that we know of could evolve and adapt to coexist with this nanopeptide. How can we be sure? Isn't evolution in Darwinian terms something random and unpredictable?
It's not something that I can predict because, of course, microorganisms are very diverse, and I can't speak saying that all the microorganisms will be non-resistant. But big groups of fungi and bacteria has been studied, so I can say that at least many pathogens within those groups that are important pathogens for humans are very low probable to become resistant, let's say. Yeah.
Good. Fantastic. Thanks very much, Miguel.
Thank you very much.
Congratulations. Let's break the wall of implantable sensors with Jillian, Tricia, Gamboa.
I'm gonna let you in on a secret. Although I'm a biomedical engineer, I've always wanted to become a doctor, but I'm absolutely terrified of needles. And I discovered this fear during one of my first few blood tests. So I've always wondered how great it would be if instead of going for a blood test, you can just easily get a text telling you how your body is doing. Well, lucky for me, this is one of the many possibilities of implantable sensors. These are devices that can be placed inside the body in order to monitor different physiological conditions. It's like shrinking a thermometer, placing it inside your body to monitor your body temperature. These devices are very useful for patients with diseases or injuries that require constant monitoring. For example, monitoring the glucose levels of diabetes patients. So these devices are very complex and are composed of several parts, one of which is the electrode. The electrode captures the signals inside the body and sends it over for signal processing. Normally, these electrodes are made of metals, but metals tend to be stiffer compared to the tissues inside the body, and this can cause the implant to prematurely fail. And now this is where my project comes in, because my end goal is to address this problem through the use of conducting polymers. These are materials that are very interesting because they can be placed safely inside the body, they have the natural ability to conduct electricity, and they can be manufactured easily and inexpensively. More importantly, they can be easily combined with other materials to further fine-tune their properties. So in my case, I will be combining conducting polymers with hydrogels, which are gel-like materials that can hold large amounts of water. Because of this, they can better mimic the softness of the tissues inside the body, thus overcoming the stiffness limitation of metallic electrodes. So in essence, my project is like giving a piece of gelatin the same electrical properties as that of copper wire. And this is where the biggest challenge of my project comes in, because the conductivity of conducting polymers is still lower than that of metals. In order to overcome this, I plan to add other materials into the conductive hydrogel in order to improve not only its conductivity, but other properties such as flexibility and strength. Ultimately, this hydrogel-based electrode can pave the way for long-lasting implantable sensors, making healthcare less expensive and less invasive in the long run. And for people like me, less encounters with needles.
How do you do, Jillian?
Good, good.
Fantastic. Alain Fuchs,
Hi.
co-chair of the jury, would like to ask you a question.
Hi, good morning.
Good morning, Jillian.
It works. It does.
It does work. Thank you very much for your pitch, which was extremely interesting, really. My question would be, these sensors actually do experience some degradation with time, I believe, even on the long run, you know. So my question is how do you tend to control the rate of degradation of your sensors?
Yeah, so actually one of the features of the sensors that we're trying to build in the ITN is actually that it's bioresorbable. So that in the future, after the sensor is done sensing or monitoring the diseases, it can naturally degrade. So one of the things that we could do for that is to control the rate of the degradation of the hydrogel itself and the other materials by adding or by controlling the cross-linking of the hydrogels or adding other materials that can prolong its life inside the body. So it's more of like a mixture of the things that we add into the material to control the rate of degradation.
Thank you. Thank you very much.
Thanks very much.
Thank you.
We have a question from the audience. Could you explain what problems you still have to solve for your idea to be definitively operational?
Yes, so like what I mentioned in my video, that the biggest challenge is to give the hydrogel the same conductivity or electrochemical properties as that of a metal. But I think that it doesn't have to be 1:1. It just has to reach the specific electrochemical level that is needed for the application, whether it's for an electrode or whether it's for an electroconductive scaffold. It doesn't have to have the 1:1 metallic properties. So I think that that is the challenge. That is why I want to add other materials into the hydrogels other than the conducting polymers to further increase the electrochemical properties.
Okay, thank you very much, Jillian.
Thank you, everyone.
So let's break the wall of inflammation caused arrhythmia by Thomas Hutschalik.
I want to talk to you about rhythm, heart rhythm. If you stick your fingers in your ear, then you'll hear this sound. Don't do that right now, I still want you to listen to me. From the day we're born until we die, this sound sticks with us. Your heartbeat, right there in the background. Now, imagine this is what you hear. That's an irregular heartbeat, an arrhythmia. And these diseases can be devastating, scary, and some are deadly. The most common one is atrial fibrillation, which affects millions of patients in Europe and takes up 1% of the EU's healthcare budget, 10 billion euros. But what causes the heart to become arrhythmic? Well, we have the culprit right here, right? The heart muscle cell, the one who's contracting and doing this beating, right? Well, what if it's not to blame? What if there's someone else? In the heart, we have several different types of cells, neighboring cells that surround our beating cardiomyocytes here. And if you've ever had a noisy neighbor throwing parties at night, you can definitely see how a neighbor can mess up your work. One of these neighbors is a type of immune cell, and immune cells can cause inflammation. And that's what I want to talk about with you. Inflammation caused arrhythmia, or as I like to call it, burning hearts being offbeat. So what is it that I do? Well, I use human stem cells in the lab to create these contracting heart muscle cells and these immune cells, and I bring them together and see how inflammation can affect arrhythmia. And what I'm able to see in the lab is that, yes, inflammation can cause irregularity in beating. 15 years ago, we wouldn't even have been able to do these sort of experiments with stem cell-derived cells. And it's just currently that we're starting to investigate how inflammation can cause irregularity in beating. But just knowing that isn't the important part. What's important is that we can use this knowledge to find new treatments for patients with atrial fibrillation. So for example, in my research, I was able to show how some anti-inflammatories can reduce arrhythmia. And this is just the first step in finding new treatments for patients. giving them relief from the disease and lowering the burden of atrial fibrillation on all of us. And with that, I hope to help our hearts stay on beat. Thank you.
Come with us, Thomas. How do you do?
Good. How are you doing?
Fantastic. So we have a question from a member of the jury, Céline Bégy.
Yes. Thank you for your presentation. A short but technical question. How are you selecting the molecule to test, and which are the main criteria?
So the medication to reduce the arrhythmia, you mean? Yeah, so in the early stages I starting testing medication that can affect inflammation broadband. So for example, glucocorticoids. If you've ever had any sort of inflammation, you might have taken hydrocortisone, something like that. And there it is, the reason I use that, because it affects a lot of different things. So I started casting a wide net, seeing what could have an effect. And now I think in the work, the goal is to find something that very specifically only affects arrhythmia. Because you might know hydrocortisone, things like that have a lot of side effects, but we want to find a specific anti-inflammatory that only affects arrhythmia and leaves all these other side effects to the side.
Thank you.
So here's the question from the audience.
Yeah.
Your idea is to treat arrhythmia caused by inflammation as an inflammation. Why hasn't this been done before?
Yeah, that's a very good point. Let's pick atrial fibrillation, because I mentioned that. And that is a very complicated disease. And currently we have treatments. And these treatments are, for example, making a scar in your heart. When your heart is beating irregular, you then make the scar, so the beating is more controlled in one direction and doesn't go crazy all over the place. And that has worked in some parts, but over time, you see the effect of that goes away. And inflammation is only currently being investigated as a possible cause. So let's say 20 years ago, you wouldn't think of this disease as inflammation caused, but just electrophysiological or morphological. So it's just in the beginning now as a possible target.
Thanks very much, Thomas.
Yeah, thank you.
And I will hear from Marie Jarrell. She's breaking the wall of the virtual human divide.
Let's talk about societal biases. You know, racism, sexism, basically any type of bigotry. We've seen people combating biases and prejudices of all kinds in just about every corner of the world. Well, I want to let you know that we've also been combating them in the virtual world. See, thanks to research using systems like the Oculus Rift or this HTC Vive, we've found that people carry their real-world biases with them into virtual spaces, and that they impact people's virtual interactions and experiences. But this actually may be a good thing, as we've also discovered that controlling avatars of different races, genders, and ages can reduce people's biases against real people, thus providing us with multiple new interventions for combating bigotry. But VR systems like this are a bit complex and a little unruly for the average person. However, we do have a much simpler alternative, one that you likely already have in your pocket right now: the smartphone. See, every day, over 100 million people use virtual reality on apps like Snapchat and Instagram. They are able to augment or change their faces with photo filters instead of controlling a fully virtual avatar. These augmented reality or AR filters can do everything from applying makeup or dog ears to fundamentally changing aspects of a person, like their age or their gender. And if controlling fully virtual avatars can reduce people's real-world biases, imagine what these far more personalized AR manipulations are capable of, or what damages they could do if applied or used improperly. Unfortunately, we have little to no research on virtual reality bias reduction that uses AR filters, despite the fact that, as I mentioned, this technology is already being used every day by hundreds of millions of people. This is why I'm studying the use of AR photo filters for bias reduction, so we can see if these filters can not only change how you see yourself, but how you see others.
Hello, Marie.
Hello.
How'd you do?
Very well.
Fantastic. Céline Bégy has a question for you, for them.
Yes, you said that you study the use of AR photo filter to bias reduction. What is exactly the field of your researches? And in 2 words, can you explain how you do it?
Like the field, or like how we're. Well, right now we're basically looking at simple applications in like play or very simple use. So you take out your phone, you can like open Snapchat, you can put on a filter and just like look at yourself. And then we will ask you some questions about like, how do you feel about these different stereotypes? Or how close do you feel to different types of people? And seeing if like the filter impacts that, because we already have some research, like I mentioned, with the fully immersive virtual reality where you put on the headset and you're in a whole virtual world, and there have been like changes in how people perceive others and how close they feel and how much they kind of agree with or disagree with different different stereotypes. And that is kind of what we are basing like some of the research on. There's a possibility of taking it like to another level, because now with the huge use of Zoom, you can actually add filters to your Zoom camera. And there is for example, the Snap camera application, and you can do a lot of the same things there. And some people, they've used it for meetings. You can use it like to have schools. You can just use it to talk to your friends. So there is the possibility of exploring the use of filters in like those situations as well.
Thank you.
Good. Here's a question from someone in the audience. I found it very interesting, your statement that the virtual bias reduces bias in real life.
Yes.
So how do you explain this phenomenon?
Well, the thing is that our brains actually perceive a lot of virtual things the same way we perceive the real world. And it's not just virtual reality, it's movies, it's books, it's any kind of media, because we are able to connect and care for things, even things that aren't real. Like, we've seen so many Disney movies where it's a toy, or it's an animal, or even a rock. You can make a person cry about a rock that was abandoned by a child, because we are very empathetic. So even though you are dealing with avatars that are virtual, if people connect with and they identify with the avatar, and they are like, this avatar is just like me, and this avatar also looks like this person in the real world that I see every day. And if the avatar is like me, maybe this person is also like me. Maybe we're not so different. So this is kind of what we like have found just in any type of identification or representation research, and using fictional or virtual beings to impact how we see the world.
Okay. Thank you very much, Marie, for this presentation. Ricardo Leonel Marroquin Pais tries to break the wall of unsafe drinking water.
Hey, today I would like you to think about the water we drink. There is nothing like a glass of water when you're thirsty, right? But what if I tell you that, besides being refreshing, it can be slightly toxic? Well, it actually could be, and you won't even feel the difference because it will taste exactly the same and it will look as clear as always. But yeah, it might be unsafe. And to understand how this happens, we have to take a look to the water cycle. We often obtain the water that we drink from rivers or lakes. Here we can observe part of the Lake Mälaren in Sweden that supplies water to the beautiful city of Stockholm. But before drinking the water, we must disinfect it to remove pathogens and bacteria. However, if the water quality in the source is bad, not everything will be good news during the disinfection. Toxic compounds can then be produced, which most likely will end up in the tap of your house and ultimately in your body. When we consume this water for many years, these compounds have been found to lead to various forms of cancer and to produce fertility problems in women. This is something really important to be aware of, and lately it has become an emerging concern. In fact, 6 months ago, Ireland was referred to the European Court of Justice for supplying of unsafe water to a portion of its population. But how can we solve this? Should we explore other sources? Should we change our treatment methods? Possibly, but that will require huge amounts of money, energy, and time, and we wouldn't even know if that will guarantee the results. That is why we thought about something more accessible: quality forecasts. Yeah, looking at the future. Currently, many water systems operate without knowing enough about the water quality before treatment, or simply the monitoring time takes way too long. So we propose a forecasting system that works with climate data obtained from global datasets which are publicly available. This data is then processed by mathematical functions to simulate hydrological responses and estimate water quality parameters. For instance, we can simulate the concentration of certain pollutant or nutrient in a river just by knowing little more than the temperature and rainfall of that area, which is really great, because then we can estimate not just the present but the future water quality of that river under different climate scenarios. This will allow us to improve our treatment right away. For instance, dosages in a plant will now be based on short-time generated information, so they will become more accurate, resulting in safer drinking water. The advantage of using this system is that it can be implemented in any part of the world with direct management applications. This way, we can ensure and supply of water to our generation and to the ones to come by a faster, cheaper, and worldwide accessible approach. And this is how we can break the wall of unsafe drinking water.
Hello.
Hi, Ricardo. How do you do?
Fine. You, how are you?
Fine. Thanks very much. So, Anwesh Bhattacharya would like to ask you the first question.
Okay.
We don't have, we can't hear you, Anwesh. Could you repeat that, please?
Sorry, am I audible right now?
Yes, fantastic.
Right. So thank you, Ricardo, for your interesting pitch, which has a wide domain of being used if solved. So first question for you is, does your forecasting method have all the essential parameters that you need to accurately model the water composition at any place? And I have a follow-up question here.
Well, that depends on the area, because some regions are struggling with high agriculture, for instance, and in those cases, you will need to monitor different parameters as derived from fertilizers. However, currently we are monitoring more organics, which are more depending on the natural conditions of the landscapes that are problematic for countries as Ireland, Sweden, north of Europe, and Spain. And it actually depends on the location and what are the anthropogenic and natural factors influencing the water quality in those settings, plus the climate change projections that we use to predict the impacts on the water bodies in that region.
Right. And the follow-up question is, how will your solution solve the quality of the treated water itself? Thanks.
Well, what we are aiming in the current research is that with this forecast that are aimed to be in a short term, in a daily basis, we will then inform the water operators of the water treatment plant for them to know what is the water quality in a week or 2 weeks after this date, for instance. So they now will prepare their methods in advance, because currently what they do is that they just have some rough indicators. It depends on the water treatment actually, but usually they just have some rough indicators, and they don't put dosages of disinfectants or any other coagulants, for instance, in a accurate way. So that is how that's how we can actually inform them.
Right. Thank you very much.
Thank you very much, Anwesh. Here's the question from the audience. Would this technology also work in predicting industrial pollution of drinking water?
Yes, it can be applied to that. We are not currently aiming for that, but the procedure won't be very different, because at the end of the day, some industries have just different substances, so other parameters will need to be monitored in order to know that. And for instance, as I said, a lot of anthropogenic sources such as agriculture are very intensive in some regions of the world, and the amount of nitrogen or sulfates coming from fertilizers can be of great interest of monitoring in those areas, and could serve as a basis for short-term adaptations in the water treatment and also long-term adaptation for climate change scenarios and policymaking.
Okay, thanks very much, Ricardo. So let's take a short break, a 7-minute break. We'll be back, just very small technical break. We'll have a longer one later on, and so we'll be back at 10:40, okay? We'll see you then. Welcome back, everybody. Let's move on to our next contestant. His name is Austin Madison, and he's breaking the wall of gene-activated biomaterials.
Have you ever received gene therapy? No? Now let me ask you a second question. Have you ever received a COVID-19 vaccine? Yes? Then you may be one of over 5 billion people worldwide that have had at least one vaccine, many of which use gene delivery technology. Gene therapy can be the adding, altering, deleting, or splicing of a gene. Genetic cargoes are directed towards a target cell in the body to drive a therapeutic health benefit. For select COVID-19 vaccines, they deliver messenger RNA to the cytoplasm to induce an immune response and protection from sickness. It seems straight out of science fiction, yet it has transformed our world in the last 2 years. Once out of reach, and controversial or not, gene therapy is here to stay. In the 1990s, it was a promise to target untreatable conditions, but low efficiency, high toxicity, and failed trials led to the halt on global research programs, until now. Implementing RNA vaccines for COVID-19 has opened the world to possibilities. So today, I am overcoming previous challenges by using gene therapy technology on materials for health applications, or biomaterials. I'm a biomechanical engineer, and I develop biomaterials to repair complex bone fractures and regenerate cartilage from advanced joint disease, commonly known as osteoarthritis. These customizable collagen-based biomaterials are also known as scaffolds, and once implanted into the body, they behave like sponges. Drawing in cells and fluid, these templates guide the repair and regeneration of bone and cartilage so that it functions like new. And unfortunately, for patients with pre-existing conditions, poor health, and for large defects, these traditional techniques and materials are not adequate for the healing to occur. So in my research, I'm using non-viral nanoparticles to deliver therapeutic genes on these biomaterials. when the gene-activated biomaterials are implanted, the body is instructed to produce therapeutic factors that boost the healing power of the implants. My work overcomes previous challenges in gene therapy. The treatment is localized, which increases effectiveness and reduces toxic effects. The cells are instructed to gradually release therapeutic factors that support the regeneration of tissues from patients that have complex disease conditions. I am breaking the wall of gene therapy to develop materials that will one day replace the need for joint replacements.
Austin, come with me on stage. Thank you for making it to Paris. Julia Rocco would like to ask you the first question. She's a member of the jury, and she was a finalist of the Falling Walls Lab MSCA 2021 last year. Julia.
Yes, thank you, Austin, for your presentation. I would like to ask first a curiosity. So which therapeutic factors are released? And then I would like to ask if you have already run a pilot study. And if so, if you could quantify the advantages of this new approach in terms, for example, of reduction of healing time or lowering of toxicity or whatever you want, like to demonstrate that it's advantageous.
Okay, great. Yes, so the therapeutic cargoes that we're delivering, so specifically for my project, one of them is called, it's the genetic encoding for a protein called lubricin. And in the case of cartilage repair, lubricin is present on the surface of cartilage. So when you want to repair cartilage, you want that surface layer of the healed tissue to produce this protein. And lubricin functions that it lubricates. So the way that we are evaluating this in our in vitro studies is we look to see how well these implants lubricate in mechanical testing. So that's one of the methods that we evaluate the effectiveness of the delivery system. And other ways we would evaluate it is the ability for these therapeutic factors to drive a specific regeneration, so into the cartilage lineage. In the case of, I work with predominantly stem cells, so we want them to become more like cartilage cells, chondrocytes.
Okay. Here's the question from the audience, Austin. With this technology, would there still be a risk of tissue rejection, as often happens with organ transplants?
So far, these collagen-based scaffolds have already been implanted in humans in other clinical trials. So they've seen quite good success thus far. There is the potential for some kind of toxicity in the case of adding therapeutic genetic factors. Although we have done quite a few studies in animals thus far, and there's shown a lot of promise. So the toxicity is quite low because we optimize the dosage so that the therapeutic benefit is reached with a minimize on any added toxic effects.
Thanks very much, Austin.
Thank you.
Bravo. So there's someone here in this room who sends me the question. It's Gerard, who is right here, and he tells me that the audience on the chat is sending a lot of support for you fellows. So you have to know that you're very supported by the audience here and the people abroad who is on the chat. And some say that you are all doing great, and it's going to be very hard to choose the winners. Thank you, Gerard. Let's break the walls now, the walls of sensing, with Marco Perestiuk.
What if I tell you there's a virus in this room? Well, first of all, probably you will immediately think about COVID. So let's say there's a bunch of COVID viruses flying around. How have you been dealing with this throughout the past years? Well, all of us, we put sticks in our nose to get tested. We wear masks, we distance ourselves. But if you think about it, all this is good to reduce infections, but there's something much more powerful, much more efficient and much more convenient that we could do. Only if we could sense COVID in the breath of someone. Be able to say, the air coming from the person next to you indicates that this person has COVID, danger. Now imagine we would have a chip in our phone that could sense COVID or anything dangerous for us. And then be able to say, okay, watch out, or if we've just tested ourselves, go and isolate yourself. And now think about it, we would have such a chip 2 years ago. Well, that sounds pretty good, no? So, welcome to the world of sensing. We want to sense the world, because in the end it always comes down to the same thing. We want to detect something in the air that we cannot see. No matter if it's COVID, no matter if it's air pollution from cars, no matter if it's a dangerous gas leak. We want a one-size-fits-all type of solution. So I was telling you about chips. So why do we want to use chips for this? What's so great about them? Well, the answer is pretty simple. They're pretty damn small. We don't want these huge air quality monitoring stations that we have right now like this. We want something tiny. Think about it. Right now you all have electronic chips in all of our devices. All of your phones that you have in your pocket are more powerful, a million times more powerful than the computer used for the Apollo 11 mission control. But what your phone cannot do is it cannot sense anything. For sensing, we need a different kind of chip. We need a chip working with light, because light is perfect for sensing. In principle, light passes through some molecules that are dangerous. We detect it, we get a warning, watch out. Nothing is there, green light, everything is fine, right? So my job is to build a chip that traps light for sensing. That traps light in rings like this, on tiny chips like this, that can in principle go into all of our phones. We want to make sure that soon all of you cannot sense only COVID, but the world. So if you want to be among the first ones to have a light chip in your phone, please follow us on our project website. Thank you.
Hello, Marco.
Hi.
Come with me here on stage. We are having a question by Marina Rantanen-Moder. Could you tell us about you? You are on the board of the MSCA.
Yes, so I'm here representing our chair, Fernanda Bajanca, who unfortunately couldn't be here as of now, but she has prepared all the work and I'm a spokesperson for her.
Fantastic. Thanks very much for making it.
Thank you. Yeah, and thank you for giving this elegant description of how we can use sensing to improve our everyday lives. What I would like to ask is, what are the biggest challenges that your project will address technically? So basically, what do you need to do to realize these fantastic little chips that you're talking about?
Yeah, basically, it's kind of like a three-part problem because we need to put everything on a chip that is needed. So I told you, okay, we can use light to sense, but what do we actually need? We need a light source on a chip. So we need some sort of really bright and powerful light source that we need to put on a chip. We need to somehow make the chip interact with the molecules. And then we need to detect the light, and everything has to go on a chip. So these are basically the three problems that we need to address separately. And I would say the most difficult one is the light source, because it has to be very, very small but powerful. But I think we can do it, because basically electronics has shown us the path ahead, how we can integrate a lot of things, and I think we can do the same with photonics.
Okay.
Thank you.
We have a question from the audience, but maybe did you just answer, would this technology work in the dark?
Yes, absolutely.
The person says, okay, it's an obvious question.
No, absolutely, because the light should, it's not that we are detecting the light that you see from there. We have a laser, in fact, on our chip.
Okay. Is it a visible light?
No, it's not visible. Exactly.
So it's very powerful, but you don't see it with the
Exactly,
with the eye.
exactly.
Okay,
so you don't see anything. It's just a different color, but it's not something that our eye can see. It's in the mid-infrared wavelength range. So yeah, you don't. In principle, you should not have to worry about anything about providing an external light source. Everything should be on your chip.
Fantastic. Thanks very much, Marco.
Thank you.
Thanks very much. Kandel Shafike wants to break the walls of biosensing.
Have you ever wondered, why is it that some people are more likely to gain weight than others? Well, for a long time, we have debated obesity the same way we did our nature-nurture debate. Is it our genetics or is it our behavior in food and calories intake? Well, I'm here to tell you we're missing a third, which has been completely ignored so far, the microbiota. The microbiota is a set of all the microbes that live in our body, and around 95% of all those microbes are in our gut. We even have more microbes than human cells. Your gut microbiota can weigh up to 2 kilograms, so remember that next time you stand on a scale. Those microbes are there for a reason. We need them to be healthy because they play an important role in several functions of our body. And there is more and more scientific evidence showing that when our body is not entirely healthy, our microbiota changes as well. And that is what happens in obesity. We all know that obesity is a massive problem. It affects more than 13% of the world population. This means 1 in 8 people. Obesity has a really negative impact on people's health, finances, social life, and it means a real burden in healthcare system. It is known that obesity has multiple causes, but since the gut microbiota is altered in obesity, the role of these microbes might be really important. So an intriguing question here is, what if we could change? What if we could modulate in a predictable way our microbiota composition? Would it be helpful for obesity treatment if we could make this altered microbiota healthier? Well, this is what our project is trying to figure it out. There are beneficial bacteria that produce substances that could in fact modulate and regulate the gut microbiota composition. And by using these good microbes, we want to study if it is possible to improve the quality of gut microbiota in obesity, and together with that, if it is possible to improve the general outcome of obesity treatment. So remember, not everything's about our genetics and not everything's about the calories. We are not alone. We really need to mind our microbes as well. And through our microbes, science might help to break the walls of obesity.
Natalia, it's good to have you here. Of course, I got it wrong. Okay.
No worries.
Okay, thanks very much. So yes, you wanted to break the walls of obesity, and you are Natalia Soledad Rios Colombo.
Same. The very same.
And you are using this player, which has been around for ever, microbiota, as you just mentioned it. But we have already, we only discovered its role quite lately.
Exactly.
Exactly. Okay. Marina Rantanen-Moder is here to ask you the first question.
Okay. Yeah, thank you. Super interesting. Well, the question is, because microbes have been known for a long time, and it seems that the relation to obesity also has been known for some time. So exactly what is the unique contribution and the novelty of your work?
Well, actually, it hasn't been known for that much time, the relationship between the microbiota and obesity, and also metabolic syndrome and diabetes. Like, we're actually, like, if we look at the temporary line, we're like just discovered that yesterday. We in our project, we're particularly analyzing, there are a lot of research undergoing about changing or modulating gut microbiota to address the treatment of several diseases, but we're studying a particular group of microorganisms that are bacteria that produce these substances that I was talking about, that are called bacteriocins. And there isn't much research about how bacteriocins, that are small peptides, that some of the bacteria that are in our very same gut can actually contribute to modulate the gut microbiota. So that there is where our research is actually like innovative, because there isn't much research about how these peptides can actually contribute and how this particular bacteria can actually improve the metabolic profiles in obesity, or can cause a possible reduction in weight gain in animal models. So this is what it is, innovative and new about our project.
Thanks.
You're welcome.
Natalia, when you change the microbiota equilibrium to treat obesity, how do you make sure that the other useful functions of our microbiota are not affected, like immunity or the digestion of certain foods?
That is what we're trying to figure out in our project. It's like we're trying to actually assess if the changes are for better and not for worse. But like we normally use these bacteria that are grass bacteria, generally recognized as safe. So these bacteria have proven effects of, like they have proven to be healthy if we consume them. So it's really something, a fashionable topic, because like now yogurt and fermented foods are becoming really fashionable, but because of all their properties and because they have these good bacteria that have proven safety and effectiveness to improve our general health.
Fantastic, thanks very much,
Thank
Natalia.
you. Thank you so much.
I think you are already aware that Kandel Shefiki is trying to break the walls of biosensing.
What if I give you a chemotherapy right now? Have you ever thought of getting the medicine for the disease that you might have in the future? It sounds so unreasonable, whatever I just said, but this is what that is happening around us. Bovine mastitis is a disease that affects milk-producing glands of cows. The main problem with the disease is that it cannot be detected until it reaches its very late stages. So the only option left is culling or slaughtering a cow. How unfortunate is that, right? Farmers, left with no other option, then decide to give antibiotics to the entire herd of cows without any evidence of mastitis. What does that mean? It means that even the healthy cows are getting medicines. It seems so unbelievable, right? But this is what that is happening. But the story, it does not end here. Antibiotic residues, they go inside the milk samples and can affect the consumer's health. And at the same time, they can be released in soil and in water, together contributing to a bigger issue of antibiotic resistance. Can you believe that drinking this one glass of milk can kill you in future? Economic burden associated with mastitis cannot also be overlooked. It costs a hefty amount of 2 billion euros every year in Europe. Current methods to diagnose mastitis are time-consuming and are expensive. But at the same time, they are not able to detect the disease at those early stages, when animals are highly infective and treatment therapies could be most effective. My device, BioSense for precision mastitis, will be able to identify mastitis at those early stages by detecting the biomarkers of early immune response of cows. MicroRNAs, cytokines, antimicrobial peptides are some of those biomarkers that my device is going to detect. Our new technology will make on-site testing of milk samples possible, and that too at a very low cost. And we can do that, can you believe, by using our mobile devices. It will enable the constant surveillance of animals to detect mastitis, enabling farmers to do timely interventions, and all of this hugely benefiting Europeans' dairy industry. My device is so promising to use that I can fine-tune this device to detect other silent diseases like cancers, specifically renal cancers, diabetes, hepatitis B and hepatitis C. If we have a non-invasive, stress-free and prompt solution available, you don't have to get chemotherapy right now. Thanks for your attention.
Hello,
Good morning, everyone.
Hello, Candile. How do you do?
Good.
Fantastic. Julia Rocco has a question for you.
Can you hear me?
Yes,
yes,
we can.
Okay, thank you for the very interesting presentation. Yeah. So I would like to ask, like regarding the novelty of your research, where would you identify really the novelty? More on the type of biomarkers that are sensed or in the processing strategies? And then, like, how do you practically detect these biomarkers and send the relative information to the mobile phone?
Okay. Yeah, thanks for your question. First of all, the novelty of the device, I would say that the both things that you said about the biomarkers and also about the platform that I'm making, it's novel. Still now, for mastitis, there's no device that can detect those biomarkers. And the main novelty of my project is actually the sequential detection of those biomarkers. So I'm using this porous silicon platform, which has a very tunable pore size to detect those biomarkers, and that's the sequential detection. Like, for example, if I'm capturing the exosome, we are going to cleave the exosome to release its contents. That contents will go to another layer, and it will bind to that layer. So that's how we are, detecting multiple biomarkers all at one time. That's the novelty of my device. The second question was regarding the translation. So my device is going to produce this electrical signal. So that's my thing that I'm doing to produce these multi-layer structures to detect those sequential biomarkers. But the signal that will be electrical, it will be translated on the mobile device. So we have collaborations with another group that is developing a software for that. So my work is producing this electrical signal from different biomarkers. I hope that answers your question. Yes?
Yes, very clear. Thank you a lot.
Okay.
Thanks very much, Julia. Here's a question for you, Candile. The technology you described sounds like magic. Also in detecting cancer. So what would be the possibility of applying it for human diagnosis?
For human, for the cancer, So that's what I mentioned for the cancers, specifically renal cancer, that is really silent disease, or hepatitis B or C. So the device that I'm making, it has a very tunable pore size, and I can do the differential functionalizations. So to detect the other diseases is so. We need a little bit of optimization in the pore size and the functionalization, and we can detect different molecules with this device. So it's like really promising, especially the multi-layer structures of the device. Because before that, there's some work that has been done on the optical sensing, but not the electrochemical sensing. So this is the very first device.
Okay, thank you very much, Candile.
Thank you so much.
And I will hear from Elise Landers, who breaks the wall of blurry images.
I'm sure you've used a magnifying glass in your life, maybe to read small print or to put a thread through the eye of a needle. Magnifying glasses, as we all know, can produce an enlarged image of an object. But have you ever wondered what the maximum magnification is we can possibly obtain with lenses? Or, in other words, the size of the smallest object that we can possibly see with lenses? Is there a limit? Well, it turns out there is. When you zoom in too much on an object with lenses, the image will become blurry. You can compare it with an image on your phone. When you zoom in a little, sure, you will see more detail. But at some point, the image will simply become blurry. Now, the same problem appears in microscopy. And the reason is not the quality of the lenses or something like that, but it's really the physics of light involved in the image formation process that prevents us from seeing very small objects. The limit is more or less 200 nanometers. Now, 200 nanometers is 500 times smaller than the thickness of a hair. So this may sound very small, but actually it's still much larger than the size of many interesting objects, such as biomolecules like DNA or proteins. So when we want to image those and we use conventional microscopes, it's very challenging to do this. For example, here you see microtubules, and microtubules are formed by tiny proteins that form the cytoskeleton of the cell. And they are crucial components involved in many cellular processes. But when we want to study those and we use conventional microscopes, we're not able to see the individual molecules and to distinguish them, but instead what we see are these continuous blurry chain of molecules. Now, in my research project, I'm trying to solve this problem by using an imaging technique that works in a radically different way. What I do is I focus a laser beam on a single molecule of interest in the sample, and then I move the laser beam around this molecule while at the same time measuring the response of the molecule to the laser light with a very special and novel detector. And this allows us to find the position of the molecule with a precision of a millionth of a millimeter. Now, once I know where this molecule is, I can move on to the next one and find the position of that molecule. And I can repeat this process over and over again until I have found the position of hundreds or maybe thousands of molecules. And then I can simply use a computer to generate an image that has a resolution that may be 200 times better than the image with a conventional microscope. And this will allow us to better see what is happening and to better understand what is happening, and in particular to better understand how cells work. So next time that you're using your phone and you're zooming in on an image and the image becomes blurry, remember, you're not the only one with this problem. Microscopists face the same challenge every day. Thank you.
Eli.
Hello.
Welcome. Anwesh Bhattacharya has a question for you.
Thank you.
Thank you very much, Eli, for your well-explained presentation. So with your increased resolution microscopy technique, can you image a large area very quickly? Because you mentioned that you scan a specific molecule itself. And my second question is, what are the challenges that are still there in carrying out this kind of large-scale high-resolution imaging, but for dynamic samples, like where you can see motion or over time?
Yeah, those are good questions. The field of view is relatively small, but of course we can also image larger field of views, but then it takes more time. So it's always a trade-off between the size of the sample that you image and the time it takes. So coming back to the second question then, if you want the dynamics, then of course you need to have a fast imaging technique, and in that case it's better indeed to decrease the field of view a little bit as a trade-off than for dynamics. So it depends on the type of sample. If you have a static sample, then you can image large field of views without problems. It will just take a bit of time. If you want to image dynamics, of course, then depending on the speed of the dynamics, you will have to decrease the field of view that you're imaging.
We have a question. Would it be possible to watch live metabolic reactions while they happen in the cell using your technology?
That would be the dream, of course. At the moment, we're in a very early stage, so it means we have a glass slide on the microscope with a sample. Then the next step will be fixed cells, then live animals, and ultimately, of course, humans. But those are orders of magnitude more complex than what we're doing now. But it's an important first step, I would say.
Thanks very much, Jillian.
Thank you.
Jayashree Subramanian is breaking the wall of plant politics.
What is intelligence? When I ask you this, do you think of some things on the lines of IQ, EQ, ability to think, learn, adapt, or react? Judging by all of this, humans are intelligent. I mean, Marie Curie was pretty smart, right? But what about other organisms? Chimpanzees, octopuses, would you call them smart? I think yes. But what really makes it possible for any organism? Well, for most animals, it is having a coordinated system that can sense and react to your environment. I'm basically referring to the brain. And that's how my brain works. So, what's up with plants then? Could they be smart too? Well, this guy certainly thought so. Charles Darwin, the father of evolution, was pretty obsessed with plants. One of his most provoking ideas is right here. By referring to a plant root at its brain, Darwin basically referred to all plants as upside-down humans. This idea has been at the center of controversy since it was perceived. But we know that plants are capable of some pretty impressive behavior. They can send chemicals to sense environment, recognize self from non-self, kins, and so much more. Which brings me back to my original question. Was Darwin right about this too? Well, I'm on a quest to find out. Look at the picture of your surroundings. I mean, really look. Do you notice anything similar? How about now? What you might notice is that plants in nature are often found in the company of another plant. And like in all communities, these neighbors interact. When we first started looking into these interactions, we noticed that plants compete for food, resources, or space. But recently, scientists discovered that plants can also actually help each other. My PhD research suggested that this plant altruism might be much more complicated than previously thought. That plants can factor in information about the environment, about the neighbor identity, and even plant health and make these decisions. What's more surprising is that this information is somehow encoded in their DNA. So, what I am trying to answer is that are plant roots at the center of that coordinated system that we know exists in animals? Maybe I'm wrong. But any scientific advancement is driven by curiosity. Imagine if our farmers could produce double the yield in half the space involved, if we could give them an exact planting configuration for sustainable crop production. Answering these daring questions hold the key to our fundamental understanding of the world around us. The next time you take that walk in your neighborhood, I hope you take a second to remember that there is a lot of politics you don't even hear. Thank you.
Hi, Harira. Jashri Subramanian.
Jashri,
okay,
yeah.
Just like yesterday.
Exactly.
When we met on our round table.
Yeah.
Themis Christophidou has a question for you.
Sure.
Yes, I do. Thank you, Jashri, for your presentation. We knew, we had some idea about the multiple capacity of plants, all of us, but now we're learning that plants are helping each other. Could you please elaborate further on what would be the environmental impact of your research project building on this discovery?
Definitely.
And is there a practical implementation that you have already foreseen? Thank you.
Thank you so much for the question. Yes, the dream would be to be able to identify exactly the planting configuration in which we can produce half the, using half the space involved, we can produce almost double the yield. And that is because plants are somehow integrating information about where the environment that they've grown, the co-evolutionary history of existing together, and understanding the nature of the stress that their neighbor is feeling, not feeling, I mean, I'm saying feeling, but you know, nature gives you patterns, right? So understanding the stress and reacting to the stress and thereby providing help at that certain stage. This is a very basic research question that I'm answering, but to answer to your question, if we are able to translate this research into a crop, we can give farmers the exact genetic, the exact accessions or genotypes of the crops that we're trying to put in that agricultural land and probably produce double yield. That's just one of them. The second one is, we know climate change is a real problem right now, and we don't understand fully how plants can adapt or react to these ongoing and future climatic conditions. So understanding how plants are helping each other might actually help us understand how to protect these plant communities to meet the future requirements of what we need. Yeah.
Jashri, we have a question, a second question. It's good you reminded us that roots are in a non-stop underground conversation, but what about their interactions with microbes, with worms, and the other forms of life down under?
Definitely, yes.
How important is that?
It's definitely very, very important. And the reason why we have not been able to look at these interactions so far is because studying roots is not the easiest job in the world. So we are only now beginning to understand how these roots, and specifically the root exudates, have a role in not just directly interacting with another plant, but how these indirect interactions through these microbes and worms and all the communities that exist in the soil, how they are acting together, to, in a community. It's a very dynamic system that exists, and we are only now beginning to understand that, and it's incredibly exciting, actually.
It's just the beginning. Fantastic. Thanks very much, Astrid.
Thank you so much.
Our last contestant is David Cermenio Perez. He is breaking the world of biofilm in medical devices.
Biofilm. What is it? This is a bacteria. My immune system can easily get rid of it. But in nature, we find bacteria like this, protected against external threats like antimicrobials or the immune system. If we can prevent bacteria from attaching to a surface, we can prevent biofilm formation. We can find biofilm in air and water filters, as well as dental plaque, even in medical devices like contact lenses, dental and orthopedic implants. Imagine yourself, you have to go to the dentist to get one of these implants. It will cost you around 2,000 to 6,000 euros for a dental implant. But after the surgery, you are still under the influence of the anesthesia. You try to walk down the stairs, you suffer a fall, and you break your hip. It will cost you up to 50,000 euros. It is a big investment, not only of money, also of time and pain. Luckily, none of you will have this kind of bad luck. But that is the reality for over 4 million patients in the European Union. That is twice the population of the city of Paris, and it is costing us 7 billion euros per year. Therefore, there is a need for novel biomaterials that can prevent biofilm, and that is the goal of the ITM Arrhythmia, where my project is taking place. Within my project, we are developing biodegradable polymers. We can synthesize these polymers as Lego blocks. Each block will give us different properties. Therefore, we can control the viscosity, the degradation, and the strength of the polymers. But at the same time, we can encapsulate drugs, nanoparticles, or metallic ions to give antimicrobial properties to these polymers. My strategy is to use these polymers as a coating for medical devices. We were able to protect 95% of our samples against 3 strains of bacteria, especially during the wound healing process where the patient is more vulnerable. Over the time, the polymers will be degraded and it will allow a proper implant integration into the patient's body. I believe that my project can contribute to the solution of a worldwide problem, but it is also the stepping stone for the use of these polymers in other areas of interest, like drug delivery, or even make a medical device out of them. It was a pleasure to talk about my project with all of you. Thank you very much.
Hi, David.
Hello, how are you?
Fine, how are you?
All good, perfect.
Fantastic. Alain Fuchs has a question for you.
Pleasure.
Yeah, that was a very interesting presentation, David. Would you be able to elaborate a little bit on your last sentence about using this technology in additional medical applications?
Yeah, of course, yeah. Within my project at the moment, I'm trying to protect the medical devices that are in the market right now.
Right.
50% of the market. 50% of the market is covered by titanium or ceramics. So I'm trying to use the polymers as a protection layer for these medical devices. So we can modify these polymers even further to give them more properties like the strength, and we can even make the medical device out of these polymers. The advantage here is that we can synthesize these polymers ourselves, change the blocks, and we can, if it's a small patient, an infant, or if a person with osteoporosis, we can modify these polymers to adapt to that patient, given the advantage of medical, personalized medicine, especially.
Very good, interesting, thank you.
We have another question. Is there a risk that bacteria might develop antimicrobial resistance to your newly developed polymer?
It is a very good question, thank you for that. And the good thing is that we can modify the polymer, but also we can modify the antimicrobial effect that it has inside of the polymer. So we can adapt the drug inside of the polymer as well as a polymer. So we can detect the patient problem and also detect the infection that the patient is having at the moment. So we can tackle this at the same time and prevent the antimicrobial resistance.
Good. Fantastic.
Thank you very much.
David.
It was a pleasure.
Thanks a
very
lot.
much,
Thank you.
Mr. Fuchs. Wonderful. So we have met with all the contestants, and they, of course, all carry out very inspiring research. I hope they'll succeed and make some breakthroughs, of course. So can we have a big round of applause for all the contestants, please? Yes, it was not an easy exercise. Now is the time for the jury to decide who will receive the 3 prizes awarded to you today, and for you to vote for the contestant you found was the most inspiring. So now is the time for you to vote as well, and you can vote in the internet interface. Once again, you can use this QR code, get there, and you should find a way to cast your ballot. So you can use this QR code to get to the video stream easily and cast your ballot. And while the jury is going to leave the room in order to decide who the winners will be, let me have a little conversation with a special MSCA fellow. Her name is Milića Milić. Hello, Milića. How are you? Milića? Do you hear me?
Yes.
How do you do?
I am doing well. How are you?
I'm fine, thanks very much. So we're going to have a 10-minute interview so we can get to know you better. You are Serbian. You are a PhD student in Denmark, in Aarhus University. Did I pronounce it well?
Correct.
Not too bad, okay. So you're a student, a PhD student in biochemical engineering, and you're interested in biocatalysis and bioprocessing, and you won the audience prize last year, the Falling Walls Lab MSCA 2022 edition last year, didn't you?
Yes.
And you also won the 3rd prize, right?
Yes, correct.
Can you have a big round of applause for Milića Milić, please?
Thank you.
So tell us, how did you achieve that goal? How did you win 2 prizes?
Well, I mean, hard to say, but I would say that in short, I think I explained my project pretty well and at a level that everyone can understand, which the jury recognized and also the audience loved it. So what can I say?
You also told me that you always thought, okay, you always loved science, but you wanted to make science a real thing. You really wanted to explain it to everybody.
Yeah, like I've always felt somehow that scientists often get caught up in these technical terms, and then you start considering some things as self-explanatory when they are absolutely not. And I've always, like, my friends and my family are not at all from the topic that I'm doing. So it was always not challenging, but interesting for me to explain it to them. Like, what do you do on a daily basis through like simple examples and stuff like that. So for me, that became kind of something interesting. And then I saw this competition and then I was like, well, this is perfect for me.
Yes, you told me, I want my grandpa to know what I'm doing. That's how you put it. You like formulas, right? You know how to put things into words. Okay, so we're going to challenge you. So what is your research about?
So the goal of my research is basically, as I explained last year and won, is to produce FDCA, which is a chemical called furan decarboxylic acid, but none of you are going to remember this name afterwards. Why is this chemical important? Basically, this is a building block of a material, which is a polymer that we can use instead of the PET or PET plastic, however you call it, that we use for plastic bottles now.
Fantastic.
So the goal is basically to make a new material that would be more green, sustainable, and better for the environment.
Something like a green plastic?
You could say that.
Okay. You told me it's a plastic made of sugars rather than of petrol oil.
Exactly. So if you start from simple sugars, and these simple sugars are the sugar that you put in your tea, or if you think about wood, it's also full of technically sugars or materials that you can degrade into sugars. And from these, you can make this other chemical called HMF. And then from HMF, you have a million ways, essentially, to make FDCA.
So you told me, in a perfect world, we would use FDCA-based plastic instead of PET.
Exactly, but unfortunately, we don't live in a perfect world.
Okay, not yet, not yet. You're trying to make it perfect. So when will we have the first FDCA-based plastic bottles?
I mean, there is a company that's already doing good work, basically, in making FDCA, and a factory is being built for mass production, but we don't know a lot. #company secrets. But at the same time, we don't know a lot about this process and how the process is. It's not enough just to start from sugars and then you're making something like green. But what if you're using high temperatures? What if you're using toxic chemicals to make it? Then it kind of loses the point. So the goal of my project is to establish this reaction that will transform HMF to FDCA, but in a really green, non-invasive, very mild manner using enzymes.
Enzymes, and you've just published a paper and you've been able to make an FDCA using a cascade of 2 enzymes, right? So how big a challenge was that?
I mean, it was a lot of work for sure, and it's not, I don't like to downplay, but I do want to be realistic. It's not that, oh, I published a paper and there is a green revolution coming in 3 years, Coca-Cola is calling me that I sell them my patent and everything, but it's going pretty well.
Good, fantastic. How's life in Denmark? You come from Serbia. I think you really wanted to travel around the world.
Definitely. Currently, I'm not living in Denmark. I started my PhD in Denmark at Aarhus University, and I just loved it. I mean, Denmark it was a different world. It's very technologically advanced, I would say, and the society is a high trust society, which is, I think you have to experience it to truly understand it. But currently I'm living in the north of Sweden, in Umeå, where I went for my industrial secondment.
And so you like to travel around?
Yes. Not only for work, but also privately. This is my favorite hobby, let's put it like that.
My favorite hobby is to travel around. Okay. So how hard was it to obtain an MSCA grant?
I mean, for me, it's a funny story, actually, that I applied for a different position within the same project. And then I didn't get that position, and I was kind of sad. But then came an email from my supervisor like, hey, I have a position for you in Denmark. Are you interested? And I was. So definitely for me, it's been, when you say that you're an MSCA fellow, then people are kind of like, oh, good job. And also what I really loved was that this project, the project interfaces, go Google it, please, is first of all, something that I really enjoy, like enzymes, biocatalysis, engineering, all of that. And second of all, it's an European industrial doctorate. which means that you can experience also the academic world, but also go to a company and see how things are done there.
So tell me, what would be your best advice to PhD students who would like to take part in the Falling Walls Lab MSCA competition? I know some of them are listening to us at the moment, and they wonder, okay, next year it will be my turn.
Well, a couple of pieces of advice. First of all, it's a bit strange to film this, like talking to yourself. I'm really hoping that next year it will be a live competition, because I can imagine that it's much better, like fully live, to explain your pitch and everything.
It used to be live.
It used to be. I know, I watched the previous editions. So my advice would be really to explain it as if you're talking, as I said, in my case, to my grandpa. Like someone who doesn't really know anything. Like assume that they don't know what an enzyme is, that that they don't really understand what the title of your presentation is. And definitely try to make it fun, try to make it eye-catching, and just don't be shy, I would put it like that.
Yes, you can be proud of what you did, so don't be shy. By the way, is it possible to get to meet your grandpa in order to train with him, or?
I mean, I can arrange, like,
okay,
flight tickets are not that expensive.
Fantastic. Perfect. Perfect. Thanks very much, Milića, for this little talk we just had. We just got to know you better. Congratulations again for having won 2 prizes last year. Thanks, Milića.
Thank you very much, and thank you for inviting me. It's fun to see some familiar faces. And to all of the contestants, you are all winners, as we all say, and you did a really good job.
Yes, it was fantastic. It's going to be hard to pick up some winners. Milića Milić. Okay, what time is it? It is 42, and so we're going to take a short break. Just before you leave the room, we have to tell you that we have a little game for you. It's been specially designed, and you can play it online. Okay, so you can use this this QR code to play it if you wish. The whole idea is to find hidden objects in Marie Sklodowska-Curie's laboratory. So you can go and check it. It's fun. You have to find out a few details. So it's fun. So online people, all you need to do is click on the link which is in the chat to have access to the game. And you who are here, you can use the QR code. Okay, we'll be back at 11:55. So that's a 10-minute break. And then we will have the awards ceremony starting. The jury is at this very moment is trying to decide who will be the winners. 11:55, be there. Wonderful. Here we are back for this award ceremony. Themis Christophidou, Director General for Education, Youth, Sport and Culture at the European Commission. What would you like to tell us prior to this award ceremony, which is just starting now?
Merci, Paul. Thank you, dear contestants, dear MSCA fellows. I am amazed by what you have shown us today, by the variety of your research fields, from cultural heritage to gene therapy, from gender discrimination to biosensing. I'm also impressed by your ability to present your complex work in an accessible and clear way. I have learned a lot today. Thank you for that. Before telling you who has won, let me congratulate you all. You have all shared inspiring ideas today that show us how bright you are and how bright our future can be in your hands. As I mentioned earlier, it is crucial that scientists are able to share their work and findings in a comprehensive manner. Your presentations have proven that you will contribute to citizens' understanding of how essential research and innovation are for the well-being of our societies. You will contribute to citizens' trust in science. This is very important today more than ever. Whatever the results of this competition, we are so impressed by each and every one of you. I would like to thank my fellow members of the jury, and in particular, my co-chair, Professor Dr. Alain Fuchs. The choice we had to make today with all the jury was not easy, but we found consensus, which is what counts here. Thank you, Paul.
Thank you very much, Themis Christophidou. Alain Fuchs, would you like to join me on stage, because you are the person who is going to hand the trophies to the winners. It was, Alain Fuchs, tell me, I think you just met in a secret room there with all the members of the jury during a video conference. Yes. How hard has it been to make a choice?
Extremely hard. I mean, you know, there was a consensus meeting before, and then we heard all of you. We talked and talked all over, and it was extremely difficult because all of you were absolutely fantastic. Let me say this, really. But somehow at the end of the day we have to judge, when we have to
make a choice.
To make a choice,
exactly.
And we made the choice. Themis, I think it's up to you to tell
yes,
us.
First, Alain Fuchs, can I ask you to stand here?
Sure.
Okay, I will stay here. Could you stay there at the center? Okay, wonderful. So when you hear your name, you can come here so that Alain Fuchs can give you the trophies. So let me take the first trophy. Oh, how should I do that? Okay, I'll put this there. No, it's okay, it's okay, it's okay. You need your two hands to hand the trophy ceremoniously and solemnly. Okay, here we go. So is everybody ready? Yeah. Okay, perfect. Are you eager to know the names of the winners? Yes, I guess you're. Okay. I'll move on then. First, Mrs. Christophidou, would you please tell us who won the Falling Walls Lab MSCA 2022 edition audience prize?
The audience prize goes to Alba Alvarez Martin.
Alba Alvarez Martin.
Bravo, Alba.
Thank you so much.
Alba, would you say a few words?
Yes, sure. Well, thank you so much, all of you, and also to all my colleagues. It has been a fantastic 2 days to meet all of you, and I hope that we can keep in contact. So, yeah, thank you so much for organizing.
Thanks very much, Alba. And here's your diploma, your certificate. Alba Alvarez Martin, please, everybody. So I'll take the second trophy. It's now time to hand the trophy for the Falling Walls Lab MSCA 2022 edition, third prize. Themis Christophidou, who won the third prize?
The third prize goes to Jillian, Tricia, Gamboa.
Congratulations, Jillian. Yes, Victor. Congratulations. How do you feel?
Oh, really great. I'm super surprised. Thank you for the really great event, for the organization, and it's so nice to meet everybody. And yeah, I hope we keep in contact. Thank you.
Okay, let's do that. Fantastic. Bravo, Jillian.
Bravo, Jillian.
Jillian, I will need to come back so you can get your diploma. now is the time to hand the third trophy that goes to the second prize, the Falling Walls Lab MSCA 2022 edition. Second prize, Mrs. Christophidou. Please tell us who won the prize.
And this goes to Miguel Fernandez de Ullivarri.
Miguel Fernandez de Ullivarri, breaking the walls of antimicrobial resistance. Miguel, and not Miguel.
Miguel.
Ah.
It's always the same. No worries.
Está bien así.
Thank you.
Just a picture.
Oh, yeah, sorry. Yeah. Thank you very much.
There you go.
Oh, well, I'm shocked, actually. It was because all the videos and the answering session were very good, actually. All my colleagues are like professionals. And thank you for this, and I hope we keep in contact with these amazing people that I have met here. Thank you very much for everything.
Congratulations, Miguel. Just before you leave, did you know that this year, not only the first prize goes to Berlin to participate in the grand finale in November, but also the second prize. Okay, this is our final prize, the grand prize, the first prize. Let's move to the first prize.
And the first prize goes to Thomas Hutschalik.
Congratulations. Little picture, please. Thomas, you are going to Berlin in November.
Thank you. Well, I'm really amazed. I've never signed up for any competition like this. Like you said, I think like all the pitches were amazing. I'm really thankful to Personalized AF, my network, Encardia, my girlfriend for checking my pitch. But yeah, I'm super glad that I made it to first place. But I think all the pitches were really amazing. This is great. Yeah.
Bravo, Thomas. I think you have really shown a lot of charisma in your video. It's true, and we all remember this heartbeat that you showed. Here's your diploma.
Thank you.
We need 3 hands in, during awards ceremony. Congratulations again, Thomas Hutschalik. Alain Fuchs, what a competition it's been.
Fantastic. Just a word of conclusion and closing. Let me first thank Themis, Mrs. Secretary General, Director General, for having co-chaired this wonderful session and having been with us through these 2 days of the Marie Sklodowska-Curie Actions. We were absolutely proud to welcome you all. I'd like to thank again warmly, very warmly, the organizing committee who did an absolutely great work. We are very proud to have been able to welcome this MSCA meeting. That was fantastic. Today, this morning, how should I say? We loved all your presentations. They were absolutely fantastic. I must say that in a world where people are moaning, journalists are complaining, etc., it was so so nice to see that you, all of you, want to change the world. You're absolutely true. You're absolutely frank about this, and we certainly believe that you're going to change the world with all your enthusiasm, your dynamics, your talent. This kind of event we should have every morning or something like that, you know. So we're gonna keep this in our heart. There's been a recording of your, and we have your pictures. So every time we will hear people moaning, we'll say, well, let's look at one of these pictures, you know. So you all deserve a very warm thank you. Thank you very much.
Thank you very much, Alain Fuchs. What I can tell you is that I've been a journalist for 20 years, but starting from now, I won't moan anymore thanks to you.
You're another kind of journalist, not really one.
Okay, so in a few minutes, I will tell you everything about how you can go to lunch at the Cité Internationale Universitaire if you have registered for lunch. First, congratulations to all the contestants and the winners, and you've shown such great ability to explain your research and make it entertaining as well. Congratulations on such a nice time we had at the MSCA conference, to all the organizers, to the members of the jury, Themis Christophidou, Alain Fuchs, Céline Bégy, Anvesh Bhattacharya, Julia Rocco, and Fernanda Barranca, and yourself, Marina. In a few moments, we're going to have a picture with all the contestants. Okay, I think it is time for wrap up. Have the best time. Have the best of time in Paris. And see you soon, everybody. Bye-bye.
Thank you, Paul. Bye.
Fantastic. So we're going to have a big picture. All the contestants, the members of the jury, would you like to step on the stage? Alain Fuchs is already here. Céline Bégy, Marina, spokesperson for Fernanda Barranca. On fait 2 étages ou? Oui, on fait comme ça, mais c'est. Okay. So one idea would be to have the tallest ones here at the front line. Maybe we can have the 4 prizes in the center. Thomas, Jillian, Alba, Miguel. Could you come in the center? Come on stage, please. Fantastic. There you go. Here, you can come over here. Yes, we'll try, okay? Good, better. Oh, that's perfect. Marie?
Yes, where should I go?
Est-ce que vous êtes heureux, monsieur le photographe? Qu'est-ce qu'on en fait? Oops. So, second line, could you make a step forward? Fantastic. Alors, il y a Céline, on ne vous voit pas du tout, là, Madame Bégy, venez. C'est bon, là? C'est bon? Est-ce qu'il y en a qu'on ne voit pas? Oh, only one line behind, please. Céline Bégy, come forward, fantastic. Ah, Monsieur Fuchs, me prenez bien, mettez-vous bien au centre, là, vous êtes caché, là, vous êtes bien comme ça, d'accord, très bien, bon, parfait. So we need to have them laugh. We need to have them show how happy they are. Are you happy, guys? Oh, yes, so we're going to show you 3, 2, 1, your smile. Oh, yes, fantastic. We need a big round of applause for them, please. Oh, merci, en plein milieu, d'accord. Okay. Congratulations for what you did. It was fantastic. Bravo. Ça va comme ça? Perfect, wonderful. So, just the winners. Just the winners. The 4 winners, please. 4 winners, please stay on stage so we can have a... Can you make a step forward, please? Fantastic. Oh, I have here. If you can show, wonderful, perfect. That's perfect. Bravo, everybody. Bravo. Okay, it's over already. Sorry for that. But for those who have registered for lunch, you can go to, it will be at the Cité Internationale Universitaire de Paris. Eva, you wanted to tell us about it?
Yes, so we have 2 buses that are waiting for us. So if you can just follow Camille and I. Don't forget to take all your items in the lab room. And thank you very much.
Bravo, Eva. Thanks very much.